Okay, so welcome back, everybody. So far in this workshop, we've mostly measured the performance of algorithms in terms of arithmetic. And now we're lucky to have Jim Demmel, who's came up many times during the workshop, to tell us about another way of measuring performance.
Great, thank you. It's a pleasure to be here. And I have many, many collaborators. I'm going to give you some highlights of the work over a long time, and I'll have a list of them all later. I'm going to start with the motivation as why we want to avoid communication. And so algorithms have two costs, and we're going to use both time and energy to measure it. One of them is doing the arithmetic, and the other one is moving data around. We're going to call that communication. And that could mean either between levels of a memory hierarchy. So here's the simple model. You have a big main memory called DRAM, and your problem is so big, that's where it lives. And you have to move the data up into your small little cache next to your CPU before you can do any arithmetic on it. So it's moving that data over that wire, that's the big cost. And I'll have some numbers in the following slides. So that's our sequential model of computing. And for the parallel model of computing, I have copies of this, here just 4 of them, and the expensive part is moving data from one processor to another over a network. And so that is, I'm going to have different constants assigned for all of these. And this is a trigger warning, constants are going to be very important in my talk. So what I'm going to do to analyze the complexity of my algorithm, I'm going to count the number of flops it does. I'm going to count the number of words moved over any one of the wires in the previous slide. And I'm going to count the number of messages. So what's a message? It's a bunch of words packed together into a single clump that's sent all at once. So those are properties of your algorithm. And then I'm going to multiply them by properties of your hardware, the time per flop, the time per word moved, that's the reciprocal of the bandwidth, and then the time per message, that's the communication.
Sorry, this is a really dumb question, but what's the difference between like a message and a word? Both of the sequences.
So let me give you an example, which is the bandwidth and the latency of the freeway between Berkeley and San Francisco, and let's say Sacramento. So the bandwidth depends on the speed limit and the number of lanes, and the latency depends on the speed limit and the distance. So that's that's the physics of the freeway. The physics of computers is a little bit more complicated, but it's a similar idea.
What's the difference in the definition of a word and a definition of a message?
A message is a bunch of words packed together into one contiguous chunk. A bunch of cars back to back on the freeway, and it's how long, and it's the time it takes to get from one end of the wire to the other end of the wire.
So maybe the car analogy is a little flawed here because cars are not put on larger vehicles and transported all together, but messages are this kind
yes,
of
right.
packages.
But you can think of all the cars bumper to bumper moving from Berkeley to Sacramento. So yes, and so those are very different numbers, and that's the rest of the slide. I'm going to call these numbers gamma, beta, and alpha in all my later plots. And these are very, very different, and they're growing apart exponentially with time. So here's a plot going back to the 80s of what the values of alpha, beta, and gamma. And the vertical axis is how long they take on a log scale. So there are 7 or 8 orders of magnitude in this vertical scale. The bottom curve is the time per flop. It's the fastest by far. And then why do I have multiple curves here? I have the latency and the bandwidth for the DRAM going to your main memory and for going to the network. And you can see these orders of magnitude difference. And if you're running a really big program where you're running it in parallel, and most computers are parallel these days, you're going to be sending messages over a network. And there's, let me see here, 7 orders of magnitude difference in the time of a latency sent over a network and the time to do a floating point operation. So we care about factors of 10 to the 7th. And so we want to minimize that.
You're saying that even annual is even higher than the DRAM?
Yes. So it turns out they've been optimizing the heck out of, at this point in time, how fast this can work, because, it can be very wide. You can have a lot of different wires. It's a number of lanes. Yes, it's surprising, all of this. And the good news, this is data up to 2019, and in Dave Patterson's boot camp talk last week, he said a new textbook is coming out in a few months, so I will update this with data to 2025 shortly. But these trends have been going on for a long time.
It would be very helpful for me if you could briefly explain latency and bandwidth, so I'm sure I
So as I said, bandwidth is the cost per word that it takes, which is and I made the physics analogy to the freeway, if that makes sense. Whereas, if you call MPI, which is the standard sort of programming language, programming system in which you send messages in a distributed memory computer, you call MPI send, and it takes a bunch of words that you've passed in, and it sends it all at once as a message, as opposed to sending it word by word.
And the latency?
That's and the overall cost before the final processor, all those words arrive, is the latency. So the cost of sending a message, I'm going to write this down in the next slide. So let me just get there. But I also want to talk about energy, because that's been mentioned several times. So this is for a very recent Google hardware called the TPU, 7 nanometers. And so here is, again, vertical axis is a log scale. And it's the energy to do additions of different precisions, multiplications, and memory. So basically, it's 45,000 times as expensive in energy to go to your main memory and get a word, 64 bits, as it is to add two 8-bit numbers. So we care about factors of 45,000. And if you're doing regular old 32-bit floating point, it's 900 times as expensive. So there's a huge gap in energy. And this is why all the vendors are building their new matrix multiply libraries, their BLAS libraries, simulating high precision using low precision, because it's so much cheaper to fake it, to fake 64-bit arithmetic than to actually implement it. So they're all doing these approximations, and that's another whole talk that I won't go into right now. But it's affecting error analysis. So here's our goals. We want to redesign algorithms to avoid communication between all levels of the memory hierarchy, because there are multiple levels, L1 cache, L2 cache, DRAM, going between different processors over a network. And we want to attain lower bounds, if possible. So, and it turns out the classical algorithms that we've used for many, many years are often far from the lower bounds. And so there are going to be large speed-ups and energy savings possible. So I'm going to spend most of my talk on that. We'd also like to automate the implementation of these algorithms. And it turns out the compiler community is already starting to do that, and to take some of the theory that we've developed and automate it. And I'll do a demo from their webpage of how they do that. And that we also want to adapt to ongoing changes in hardware. And so if you went to some of the bootcamp talks last week, it turns out that in modern hardware, the cost of going to memory depends on whether you're reading memory or writing memory. And reading can be an order of magnitude cheaper than writing it. And so that's also going to modify the way we design our algorithms going forward. So let me just give you some sample speed-ups from the work that's come out of our group and others. So one thing we could imagine doing is taking our algorithm and reorganizing to do the same operations, just in a different order. We can do sums in a different order. And these are some of the speed-ups we got. I'm going to go into more detail on how we got a 12x speed-up. So this was over what people previously thought was the optimal way to do the usual n-cubed matrix multiply, but it turns out it wasn't, because they weren't avoiding communication. And so I'll talk about that. The same idea gives you a 100x speed-up for sparse times dense matrix multiply. All pairs shortest path, so it works for graph theory as well, the same kind of ideas, and for n-body. So the second kind of optimization is to give. So you want to compute all the forces on between pairs of particles. So gravitational force between all pairs. So n squared work. Yes.
What is the 2.5
I'll go into that in great detail.
Question.
Yes.
Speed up, I thought we are not talking about counting operations.
This
but
is
all these
time.
other aspects. Now, speed up is just time.
Yes, just time
Now
compared to the previous best algorithm. On whatever, and some of this is old data, because I'm just, and so this may be on an old supercomputer, an IBM BEP. And since I don't have time to go into all the details, I have 8 pages of references at the end, and so you can read, reference 1 and 2 and so forth to get some of the details here. So that's one way to do it. The other way is to get a mathematically identical answer, modulo round off, but using a different algorithm. And so now we have a much bigger design space, and we got, for example, I'll go into this in more detail too, a 13x speed up for doing the QR decomposition of a tall skinny matrix on a GPU, the symmetric eigenvalue problem, sparse linear algebra, a Krylov subspace method, so that's a completely different idea, and then here we're moving into machine learning. And so as I said, this is a mathematically identical answer, but the output data structure may differ. And it may be that the obvious way to do it gives you garbage because of floating point instabilities. And so there's lots of floating point stuff that we'll go on to. And finally, if all you care about is telling dogs from cats or placing ads, there are lots of different approximations that you can use, and we get a really big design space, and we get even bigger speedups. So just to give some examples of the impact of this work, we did win a Best Paper Prize for this first result up here. But I was teaching this in my parallel computing class a few years later, and one of the students thought it was a good idea, and he decided to form a startup. And he had a lot of other good ideas too, and the startup was acquired by Intel a few years later. Then, in completely independent work, Thorsten Hoffler, who at ETH, who just won the ACM Prize in Computing, which is the Baby Turing Award, took our lower bound for matrix multiply and modified the theorem to get a constant factor. I'm just going to do big O stuff mostly here. So he got a constant, and then he took our algorithm and tweaked it to meet the constant. So he hits the lower bound exactly, and that won a Best Paper Prize. And then this tall, skinny QR won another Best Paper Prize. And then we finally got it released into LAPAC a few years later. The support vector machine work won a Best Paper Prize. And the 135x speedup also did. But maybe even more interesting, it was adopted by the industry standard benchmark MLPerf. So MLPerf is kind of like the LinPack benchmark for the machine learning community. So this is now a standard technique that everybody's expected to use. OK, so I hope that got your attention. And so here's the outline of the talk. I'll spend most of it on linear algebra, matrix multiply, of course. Then I'll do tall, skinny QR. And then I'll do iterative solvers, Krylov subspace methods. And then I'll talk about how many of these ideas generalize beyond linear algebra to arbitrary code that looks like nested loops accessing arrays, where you can have as many nested loops as you like, as many arrays as you like, and arbitrary subscripts. And we can write down what a lower bound is for the communication and what an optimal algorithm is to do it. And that's pretty general. I'll show you some pictures, but I'll apply it in particular to convolutional neural nets, which most people actually implement by converting it into a matrix multiply. But you can actually asymptotically beat matrix multiply by using this other tiling. So let's go on to matrix multiply. So let me give you the lower bounds, and then I'll talk about the optimal algorithm. And so I'm going to talk about sequential n-by-n matrix multiply. Your fast memory is of size capital M. And I'm going to measure both the bandwidth and the latency. And the bandwidth is going to depend on the problem size, your fast memory size, and which flavor of matrix multiply you're doing. So n to the omega. And you can pick your favorite omega. So it's between 2 and 3. And the latency cost, this is sort of a trivial lower bound. What's the fewest number of messages I could send? Well, how big can a message be? The whole memory. So all I'm going to do is divide the bandwidth by the memory size. So that gives me kind of a no-brainer for a lower bound.
Sorry, I must have missed it, but I still don't know the definition of bandwidth.
So how many words I send between the fast memory and the slow memory?
That's bandwidth.
The total number of words move between fast and slow. And the latency is how many chunks I can divide that up into. So in other words, remember I have this separate cost for taking a whole bunch of words, packing them together into one chunk, and sending it all at once. And I'm going to count how many of those chunks there are, because that has an extra hardware cost associated with it. That's the latency. And so how do I minimize the number of messages? I want the messages to be as large as possible. That minimizes the number of them. And how big can a message be? Well, the whole memory. So that's sort of a trivial lower bound. So all the work goes into minimizing the number of words moved between fast and slow memory. Yes?
Think about it that you're sending a message and then you have to do some additional arithmetic work.
No, it's all in the hardware to actually move it across the network and go through all the circuitry to get to the other side. And it doesn't. So here's a typical example that happens all the time. When you fetch a word from DRAM, you don't just get one word, you get a whole cache line. It fetches 4 words at once or 8 words at once. Hardware has done this forever. And because it's just cheaper to grab a whole bunch of words, because that's how the hardware is built. And so, but if I could send, pack even more and fetch them all at once, and modern hardware does that, it would even be cheaper.
But I guess what's stopping you from combining two messages together and sending them all at once. You have to do something in between.
Well, I mean, the size of the message in this case, and this is more important in the case of parallel algorithms, but in the sequential algorithm, my only bound of packing information together is how big the message can be when it finally gets to the fast memory, and it can't be any bigger than the fast memory. That's the only limit. Okay, so I'll show you the lower bound for classical n cubed, and then I'll do Strassen-like. So this theorem says that the number of words moved is lower bounded by some constant times the number of floating point operations divided by the square root of the fast memory size. And this theorem was first proven in 1981 by Hong and Kung. It's been around a long time. But the new proof that I'm going to show you, as I said, generalizes to arbitrary code that looks like nested loops. And this has been, and it's attainable by tiling. You break up your big matrix into little, square root of n by square root of m submatrices, and you move those in, and you do, little sub-matrix multiplies in order to hit the lower bound. And everybody who's optimized matrix multiply has done this for decades. This is a classical thing. So the question is, how does this generalize to the Strassen-like case? Well, I certainly hope that 3 will change into an omega. It will. And what happens to the 1/2? It's going to change into omega over 2 minus 1. So that's easy typesetting, but the math is much more complicated. So if omega equals 3, it just reproduces that result. But this is the lower bound for any Strassen-like algorithm, and it's attainable simply by recursion. Because Strassen is recursive, and you keep calling matrix multiply on submatrices, and eventually they get small enough they all fit in cache, and then there's no more memory traffic while you do that submatrix, and that's what hits the lower bound. And it has a slightly different stability, but that's okay. Yes?
So just to catch what you just said, you divide until the tiles, which are
Right.
the small blocks in the original matrix, are small enough to fit in M?
Yes, and the hardware automatically will just keep them there for you. And these algorithms are called cache oblivious because your algorithm is just obvious recursion. You don't have to pay any attention at all to the cache size. And the hardware will automatically do the right thing and keep all your submatrices in cache once they're there, and you keep using them.
So in other words, you just implement the algorithm as you normally would.
Yes.
But then once you get small enough, the matrices are small enough that they'll be around in the cache while you're just doing whatever,
Yes.
however many more recursions you.
Yes, right. It'll do the right thing. Now, in practice, you don't do the recursion all the way down to 2 by 2 matrices. We just heard talk about that because it's too expensive. And so you need to say, oh, I'm going to switch to the n cubed algorithm at some point. So you have to, when people actually do this, you have to be smart enough to know how big your L1 cache is, or when it's good to switch to n cubed. Okay.
Is the unit of bandwidth cost time?
Number of words.
Number of words.
Yes. Great. Yeah. So you have to multiply that by your hardware parameter. Yeah, I'm just counting words here. And so this is valid, this lower bound, until I can fit my entire problem into cache. And at that point, the latency shrinks to 1 because you just copy all your data into your cache, do your work, and you're done, right? So there's a limit to all of these. Now, this is matrix multiply, and we of course would aspire to attain these bounds for the rest of dense linear algebra. And we can do that. And there's a paper by Olga and Ioana Dumitriu and I, which was only worried about the computational complexity, not the communication complexity. And so we showed roughly how to do everything else, least squares, linear equation solving, eigenvalue problems, and attain this n to the omega. Now, this was long before spectral shattering was invented, so the algorithm didn't have a proof in it, but it sort of sketched basically the same algorithm that Nikhil talked about. And so your first homework assignment is to confirm whether or not the algorithms in 38 attain these lower bounds, where you just do recursive Strassen-like algorithms. I put that in quotes because I think most of them are probably easy, but if it's not, you might want to publish it. I'm not sure. So, okay, so that's the lower bounds in the sequential case. So now, let me go on to the, oops, here we are, parallel case. Okay, so n by n matrix multiply, p parallel processors. So the question is, what does local memory mean? It's whatever the memory is on your processor. That's fast compared to all the memory in everybody else. So how much memory do I need to run the algorithm at all? I need at least n squared over p on each processor. I'm ignoring the constant 3 here, because I have to have enough memory to store every matrix once. But in practice, you probably have more memory. So I'm going to add in this factor, which is going to show up in my bounds, which is how many copies of the data you can afford. So c equals 1 is the least you can do. And again, I'm going to write down the bandwidth cost as a function of the problem size, the number of copies of the data you can afford, the number of processors, and which flavor of a Strawson-like algorithm you're doing. And again, the latency cost is just going to be lower bounded by the bandwidth cost divided by that memory size. And so here's the first lower bound, just on the bandwidth. And it's lower bounded by n squared divided by the square root of p times the square root of c. So if you have more memory, you can go faster. And we'll talk about it in more detail. And the latency looks like this, p to the 1/2 divided by c to the 3/2. Now, can you attain it? And the answer is yes. I'm going to tell you in some detail about this algorithm we invented called 2.5 dimensional matrix multiply. And it works for a range of c all the way from 1 up to p to the 1/3. That's the limit. And so where does p to the 1/3 come from? I'll get into that. Well, actually, what happens if you plug c equal p to the 1/3? This latency lower bound hits 1. Obviously, I can't go beyond that. But in fact, we have a separate lower bound, which is memory independent, that says no matter how much memory you have, you can't do better than n squared over p to the 2/3, which is what this bandwidth hits when you have that many copies. So that is sort of a guaranteed lower bound, independent of how much memory you have. So that is the n cubed case. So now let's do Strawson-like.
Jim, can I ask you a question about this?
Yeah.
If C is P, so you have n squared memory locally?
Well, c is going to be limited to p to the 1/3.
Oh, sorry, valid for C is P to the 1/3. Got it.
Yeah, I can't go past that. And in fact, let me just say the c equals p to the 1/3 algorithm has been rediscovered many times in history. So what was new is realizing that it made sense to think about c in this entire range. Okay, so that's the n cubed algorithm. And so here is the Strawson-like case. So what happens to p to the 1/2? C to the 1/2, you get this funny expression here. And what happens to latency? It looks like this. And again, if you plug in omega equals 3, you get what you had above. And we have an algorithm that attains it, and I'll show you performance data for both these algorithms later. Communication avoiding parallel Strawson. And again, we hit a limit. We can't have as many copies as we like, and here's the number of copies we can have, p to the 1 minus 2 over omega. And at that point, you hit this memory-independent lower bound. You're guaranteed you can't go faster. And again, both of these memory-independent lower bounds correspond to hitting a latency of 1. And again, we aspire to attain these bounds for the rest of dense linear algebra. And your homework, too, is to confirm if you use our CAPS algorithm as a black box, do the algorithms in this reference actually attain the lower bounds? So I think that's a harder question.
In these bounds, is the bound on L bigger than just the bound latency, bigger than bandwidth over M?
No, this is equal.
Oh, it's equal.
It's equal.
So
yeah.
it is enough to just think about the bandwidth.
Yes, right. That's right. But you can attain both of you. When I say attain the lower bounds, we attain both of them.
Omega here stands for not the omega of the like the algorithm. That's an omega not of a specific algorithm.
Yeah. For any algorithm you like, you can. This is what you can do with it. Any other questions? Yes.
So are all the B processors working on the same memory?
No. They're in a parallel computer. Let me go back. This is what it looks like. So everybody has their own local memory. That's the fast memory. And you have to, if this processor wants to access that, it has to send messages over the network. Yeah. So there's also shared memory computers and all kinds of other models. I'm just concentrating on these two.
So at the beginning, the input is kind of spread across the processor?
Yes. So this lower bound applies no matter what the input distribution is. If it all happened to be on one processor, then you could say, oh, I don't need to do any communication at all. I'll just have one processor do all the work and ignore everybody else. So there's an assumption here, which you're pointing out. We're assuming things are load balanced. Yeah, and I need each processor to do one piece of the work in order to minimize the amount of work. And so you need that assumption in order to hit these communication lower bounds.
And these guarantees, these algorithms allow you to also hit the parallel, the optimal work.
Yeah, right. Yeah, all of these each processor is doing n to the omega divided by p flops. Yes. Sorry. Yes.
So are you assuming that you're not allowed to repeat work?
I'm going to actually do that later, but that's not useful for matrix multiply, but it is useful for sparse linear algebra. We'll do that. And flops are cheap, so doing redundant work is okay. There's a question over here.
So CPU then has its own cache and its own DRAM?
Yeah, so each one of these processors is just a copy of this one, and they have an extra, usually there's an extra coprocessor who's responsible for sending messages to the neighbors. The hardware is complicated. This is a high-level abstraction.
I was only asking because I was wondering if the latency and bandwidth would get affected if they had to do simultaneous units.
So you're asking, I think, about the topology of this network. Who is connected to whom? And as Oded mentioned, we have separate lower bounds that are functions of the topology of the network. And so just to give a little hint, the classic matrix multiply before, which people thought was optimal, only needed a two-dimensional interconnect network, connected to your, 4 neighbors. But to do the new lower bound, you need a three-dimensional topology. So, but for now, I'm just going to assume everybody can talk to everybody to keep things simple.
All right, in this bound that you just presented for the parallel case, you're only really talking about the bandwidth and latency of the arrows that go between the processors. Now you're ignoring the DRAM to
right, and locally, yes. But once you get all the data on the local processor, you're going to use you're going to do the optimization that's appropriate for a single processor. And real computers are hierarchical. You have all these layers, so all of these apply kind of recursively. Okay, and so here's the lower bound, as I said, for Strassen-like matrix multiply. I think I did this before. And okay, so I'm done with this slide. So what is the benefit of these formulas? Why are these formulas the best you can hope for? They give you perfect strong scaling in time. So what does that mean? If I have a fixed problem size, n by n, and I increase the number of processors by some factor, say I double the number of processors, ideally I'd like to go twice as fast. And so you need to use this algorithm for that to happen. So I'm going to increase the number of processors by some factor f bigger than 1. What does that do to the local memory size? It makes it smaller by that factor. That means I can increase C by this factor. And if you do all the algebra, the bandwidth cost also goes down by a factor of f. So all that messy algebra I'm not going to do says that you get perfect scaling in the bandwidth as well. And the same algebra says the latency also goes down by a factor of f. So that means all 3 costs of your algorithm, arithmetic, bandwidth, and latency, all scale by 1 over f. And so that's perfect strong scaling in time. But you also get perfect strong scaling in energy. So what would the goal be? The goal would be to double the number of processors, go twice as fast, and use no more energy to solve your problem twice as fast. And that happens. So here's the model. I'm going to count each flop will have a certain number of joules it takes to do it. And we saw how much that was before. I'll count the number of joules to move a word over the network. I'll count the number of joules, additional joules for a message. It's some constant. I don't care what it is. And then, of course, I have to keep all my local memory turned on. And so I'll count the number of joules per word of memory per second, because I have to keep it turned on. And then there's all the rest of the stuff in the computer, the fans and whatever it takes to keep it running. And so I'll just add another term, joules per second. And so all of that, and it turns out, you write down the model, I won't do the algebra, it takes the same energy to solve a problem f times faster by increasing it. So how could that be? I've just made my machine f times larger. So that means it's burning f times as much power, but it's only doing it 1 f times as long. And so the F's cancel, and it's the same amount of energy. So that's perfect strong scaling in energy. And again, I have the same limit as before. I can't increase C beyond this limit and still get perfect strong scaling. So third homework, this should be pretty easy. Confirm these, do the algebra and confirm these laws.
What if you wanted to optimize on energy over time? Like you wanted to
Minimize power.
minimize power while willing to kind of keep the...
Well, what I'm assuming here is that the machines are burning power at a fixed rate because as long as they're turned on, they're burning something. And so I don't have freedom to do that. Because if I use less memory, that memory is still going to be turned on. Yeah. So actually, I should say that what do computers do in real life? They in real time change the frequency, the clock frequency, and that's because they measure the heat at each part of the chip. And they say, if this part of the chip's getting too hot, I better slow down or it'll melt. And so real computers actually, in real time, change their frequency. So saying that there's a constant speed is actually not true anymore, because they're all trying to make sure things don't melt. So yeah, this is a very simple model of what real hardware does, but it captures sort of the big picture. Yes?
Can you remind me what C is again?
Excuse me?
Can you remind me what C is again?
C is how many copies of the data I can afford to have.
Okay.
On my processor. So, yeah. So my local memory, so I need at least n squared over p memory in each processor to store all the data once. But if I have enough memory to store it 2 times or 3 times, then C will be 2 or 3.
Thank you.
Okay. Okay. So what about the rest of linear algebra? Now, if we can spend most of our time doing large matrix multiplies, which is, of course, why the BLAS 3 were invented for linear algebra long ago, we can get close to the bandwidth lower bound. So the question is, can we actually, what about the latency? And so Edgar, who's responsible for this work, tried for quite a while to get, he had a 2.5D LU decomposition. It hit the bandwidth lower bound, but he couldn't hit the latency lower bound. So what do you do when you can't write the algorithm that you want? You prove a new lower bound. And the new lower bound says the product of the bandwidth and the latency for Koleski in parallel is lower bounded by n squared, no matter how you organize it. So that means that if I increase C, I can decrease the bandwidth by a factor of C to the 1/2, as I showed, but you have to increase the latency by C to the 1/2. So that's a separate lower bound that applies to these algorithms because of the dependency structure. And now we can, as I said, we can hit this lower bound for Gaussian elimination in Koleski, but for Gaussian elimination, we can't use partial pivoting anymore. We had to invent a new algorithm called tournament pivoting, and which comes with a proof of numerical stability, but I don't have time to talk about that.
Does this mean you cannot get perfect scaling?
Yes, you cannot get perfect scaling, that I talked about before. You can get it for matrix multiply, but you cannot get it for Koleski or LU or a variety of other algorithms. Yes. And so homework 4, again, this might be hard, is does this lower bound theorem, which depends on the dependency graph, apply to other standard algorithms like QR or eigenvalue problems or Strassen or whatever?
Sorry, tournament pivoting, you can trade off bandwidth and latency however you want, so long as the graph is n squared, or you have to.
So tournament pivoting minimizes the number of messages in a way that, I can talk about that later. It's very similar to an algorithm I will talk about called tall skinny QR. So you can just wait a little while, and it uses the same idea.
You want to make L smaller, just make bandwidth be n squared over L.
Or no, does tournament? I thought he said tournament pivoting avoids the lower bound problem.
No. Tournament pivoting is necessary to hit the bandwidth lower bound. It doesn't help us, but we still have this bandwidth times latency is at least n squared, as far as we know. You don't have to do any pivoting at all for Koleski. The proof is limited to Koleski, and it's natural to assume that since Gaussian elimination is even messier, that it would satisfy the same lower bound. Okay, so finally, let me tell you what the algorithms are. So here is what people thought was the optimal algorithm for decades. It's called Summa Scalable Universal Matrix Multiply Algorithm. And so suppose I have P processors in an n by n matrix. I'm going to arrange my processors, here there are 16 processors, into a square root of P by square root of P grid. And so each processor in this case is going to own an n over 4 by n over 4 submatrix. So each square represents both the processor and the data it owns. So what I'm going to do is do matrix multiply by outer products. So what I would need to do is multiply this block of red columns times that block of blue columns and update the whole matrix, and keep doing that for all red and blue blocks. So at each step, each processor who owns a bunch of red blocks is going to broadcast it sideways. So this processor here will take that block and send it to all its neighbors. The processor up here who owns that blue block will broadcast it down to all its neighbors. Everybody is going to get a red block and a blue block from their neighbors and do a local matrix multiply, red times blue, added to green. And there's the code that does it, and you can do all the algebra. That'll be a homework assignment, and it actually hits the lower bound, assuming you only have one copy of the data. But, and to do that, how many columns do you send at once? If you want to minimize latency, you got to send the whole block to minimize the latency. Okay, so that's the 2D algorithm. What's the 2.5D algorithm? So again, I'm going to assume that I have enough memory to fit C copies of the data, and I'm going to arrange my processors into this 2.5 dimensional grid. And so I'm going to have C layers, and each layer has P over C processors broken up, into this square grid. And so here's a picture for 32 processors and 2 copies. And so let me, tell you what the algorithm is at a high level, let me index the processors by I, J, and K. And so I'm going to start where all my data is on the top layer. So this processor owns that n over 4 by n over 4 submatrix, so I only have one copy of the data. So what's the first step? Each processor takes its data and broadcasts it to everybody else in its column. So everybody gets a copy. The second step is that every layer performs one seeth of the sum algorithm. So it just does independent sums. And in this case, everybody does 1/2 of that algorithm I showed you before. And when you're done, everybody has 1/7 of all the partial sums that belong to a particular subblock of C. And the final step is just take all the data in a column and do a reduction. Add it all up, and the answer lands in the top. And so that, again, the homework will be just do the counting, and it hits the lower bound.
Jim, why do you call this 2.5?
Well, this is the 2D algorithm because it's a 2D processor layout. This is a 2.5 dimensional. And so you're saying, why isn't it 3? 3D has been rediscovered many times in the literature. And that's when C equals 1/3. So in that case, I have a cube. It's a P to the 1/3 by P to the 1/3 by P to the 1/3 cube. And people have done that for a long time, but you don't always have P to the 1/3 times as much memory. If P is 1,000, you would need 10 times as much memory. And so, but yeah, that's been rediscovered many times. And so homework 5 is, just confirm that this hits the lower bound. So now, let me show you some performance data. Yes?
What's the reasonable scaling of C to keep in my mind?
I'll show you in the next slide.
Great.
So this is some real performance data on a 64,000 core IBM BGP. And C is a tuning parameter. It turned out C equals 16 was the right number for this particular instance. And so I'm doing an 8K by 8K matrix multiply, and Edgar, who's in the audience, is responsible for all this. And this is a much larger matrix. And it's normal, and so this column is the time for the 2D algorithm. This column is the new algorithm, 2.5D, and it's normalized in time so that the 2D algorithm takes time 1, and this is how much faster the new algorithm is. So it's 12 times faster. And it's broken down into how much time is spent doing arithmetic, how much time is spent sitting around waiting for messages to arrive, and how much time is actually, shipping communication and dealing with that.
So n is the size of the matrix?
Yes, it's an 8K by 8K matrix.
And why do you have that kind of number? What does that factor as, or what's special about that?
Well,
Numbers.
They were chosen to illustrate, two particular points of interest. In this case, I think, this is chosen because you go a lot faster, right? It depends on the problem size, how much faster you go. But
So you just ran through various ends and this?
yes, right. I'm just showing you a subset of the data. I will show you more plots later.
I just was wondering whether these are special numbers or...
Well, all right, let me tell you why they're special. So look at this. The green, the flop time also went down. So how could that be? Because we're still doing the same number of floating point operations. And the answer is the local matrix multiplies were larger. And that means the local BLAs ran faster. Because you can often do larger matrix multiplies faster. So for this particular problem, we got a speed up that we didn't expect. That's why we're getting 12x. By the time we get this very, very large matrix, the flop time doesn't change. That's all the same, but we got rid of a very large fraction of all your communication. So if that's where most of your energy is going, we could have had still the dramatic savings in energy as opposed to arithmetic. And this won a Best Paper Prize. So now let me show you parallel Strassen. Yes?
Is there an additional processing cost to actually do the copying of the data?
No, that's all included. Yeah, that's a lower order term. Okay, so now what I'm doing is showing you some strong scaling for different flavors of parallel, both n-cubed and Strassen-like. And so this is a fixed matrix size of 94,000 square, so you need big matrices for Strassen to improve. And for 49, for number of processors ranging from 49 powers of 7, no surprise, Strassen, up to much larger number of processors. And the vertical axis is the effective gigaflops. That means it's n cubed divided by time. So the vertical axis is basically proportional to speed up. So that means it's a fair comparison of Strassen and n cubed. And this is the peak speed, this dotted line you could get for any n cubed algorithm. So you couldn't possibly go faster than that if communication were free. And so the bottom axis here is just 2D algorithm, the 2D matrix multiply. It's the slowest. This green one is the 2.5 dimensional algorithm I showed you. And ideally, I told you this should be doing perfect strong scaling. This should be a horizontal line. Well, it's not quite horizontal. It does fade off at some point, but it's closer to horizontal. These blue lines are previous attempts to parallelize Strassen. They're sort of hybrids of Strassen and the classical algorithm with different kinds of recursions. And then the top one is the new communication avoiding parallel Strassen, and you can see it's faster than you can possibly go for all the others, and it's nearly flat for quite a while, so you nearly get perfect strong scaling. Okay, and if you have questions about what these other ones are doing, let's wait so I can keep going. So I think that's all I wanted to say about, and this was an invited CACM research highlight.
So where does time appear on this?
So the vertical axis is the reciprocal of time, basically. So up is good. Yes?
So I guess this Cray computer you're running on has a 2.5D communication between the processors.
So let's see, do you remember?
Yeah.
What should we be thinking of? You want the fastest 2D algorithm, 2.5D algorithm, and 3D because it depends on what machine would have available, or is that control? I know that feels like a silly question, but
well, if you were on, so it turns out that the way people build accelerators these days is you're only which is on a 2D chip, you're only connected to your nearest neighbors, and they only use 2D algorithms.
I see. Okay.
Because that's what the hardware permits. But real networks where you can connect the wires wherever you want in a big data center, you have many more options.
Okay.
Any other questions? Okay. So let's go on to an algorithm where we have to use a different mathematical algorithm to hit the lower bound, tall, skinny QR. So let's suppose I have a tall, skinny matrix in 4 processors, and each processor owns 1/4 of the rows. So what's the first step of the algorithm? I want to factor this into Q times R. Without doing any communication at all, each processor is just going to do a local QR factorization. So what have I implicitly computed? I factored my original matrix into this block diagonal orthogonal matrix times a stack of 4 triangles. And of course, I don't want 4 triangles, I want 1 triangle, but that's the first step. So then I take those 4 triangles, and now I'm going to communicate. I'm going to pair up these. So I'll move R1, 0 into the other processor. And again, I'll do a local QR decomposition of that stack of 2 triangles. And again, what have I implicitly computed? I've factored these 4 triangles into that block diagonal orthogonal matrix times 2 triangles. One more step, put the 2 triangles together, do QR. And what have I done? I've factored my original matrix into that orthogonal matrix times that orthogonal matrix times that orthogonal matrix times R. That's the QR decomposition, just written in a different data structure. And so the output is actually all of that, all of those implicit Qs. So what have I done? I've just basically done, a reduction operation, where a binary reduction tree, where my reduction operation is the QR decomposition. So that's what it is in parallel. So what would I do on a sequential machine, where my cache is too small to fit the whole matrix? So suppose I can only fit, say, n over 4 rows into my cache. I'll read the first n over 4 rows in, do QR. Then I'll read in the next n over 4 rows, put R0 on top of W1 and do QR again. Read in the next n over 4 rows, read in the next n over 4 rows, and I've read this matrix from slow memory to fast memory once, and 1 is a lower bound, and I've again done the QR decomposition, but with a different reduction tree. You could imagine a more complicated data structure where I have dual core, so I could have 2 processors doing things at once, and then I have to read in stuff from DRAM and read in stuff from DRAM, so I get that reduction tree. But of course, real computers are much more complicated. You could have multiple cores and multiple sockets and multiple racks, and it gets very messy. So the idea is we can choose the reduction tree dynamically, depending on what hardware you have available at runtime. And if you're in the cloud, who knows what that will be. We'll choose that reduction tree dynamically and output the answer. Okay, so what kind of speedups do we get? I'm not going to go into details. 8x, 6.7x, 4x. 13x on a GPU, as I mentioned. This one was sort of fun, completely independent work by some collaborators. They got a 4x speed up on 4 French cities connected over the internet. And so obviously going from one French city to another, there's a very large latency, but it turned out that they could still completely hide all that by doing this algorithm. The biggest speed up was infinite. So in this case, the graduate student was trying to run a very large QR decomposition that didn't fit in DRAM. It actually had to go to disk. And so he ran the classical algorithm and it never finished. So he just hit Control C. So that's infinitely long. But the new algorithm only went 2 times slower, as though he had infinite DRAM. It almost completely hid all of the the access to the rest of the memory. And so let me also add that if you're doing the SVD of a tall skinny matrix, the first step is to do QR. And so this SVD speed up will also give you about the same speed up. And this also won a Best Paper Prize. And we got it into LAPAC in 2016. But a lot of users said, oh, we really need the original data structure, where you have a single householder vector per column. And so we had to invent a new communication avoiding algorithm that reconstructed the classical data structure, again, with a single reduction. And so we finally got that out there, too. OK, so that's all I wanted to say about dense linear algebra. And so now I'm going to go on to iterative linear algebra. And so we've already heard about this. I'm going to do k steps of some iterative solver. And I want to solve either ax equal b or ax equal lambda x. And so what's the inner loop doing? It's doing k sparse matrix vector multiplies from some starting vector. And there's a whole zoo of different algorithms for doing this. So what is our goal? It's to minimize communication. And so let me tell you what our model is. I'm going to have to make some assumptions about the sparsity structure. If the matrix isn't very friendly, this won't work. So let's assume it's well partitioned, and I'll draw some pictures of what that means. And so what's the serial implementation do? Conventionally, each sparse matrix vector multiply would require me to read the matrix from slow memory to fast memory and do all the work. And if it's too big to fit in fast memory, every time I do an SPMV, I have to move it again. So k moves of data from slow to fast memory. We're going to do it with 1 move of the data. We're going to take k steps of the algorithm and move the data just once. So how big can k be? Well, there's some limits. We'll see. So that's the serial implementation. What about the parallel implementation on preprocessors? So in the conventional world, every time I take a step, I need to do some dot products and compute some norms. And so I'm going to have to do a reduction. So for every step, every one of the k steps, I need to do a reduction, and a reduction costs me log p messages. I'm going to do it with just order log p messages. So it's going to have the same latency cost as a single step. And so there's going to be lots of speed up, and we'll show you some numbers later. We're going to have to do some redundant computation, but as we said, flops are cheap, so that's OK. But this does not work in absolute generality. If your matrix can't be partitioned well, it won't work. There are only certain preconditioners that this applies to, because preconditioners can be problematic. And if you just do it in the obvious way, which I'll start with, it's completely numerically unstable. But we can fix that. Okay, so let me start with GMRes and talk about how we're going to optimize that. And we already heard about it. So I'm going to take k steps. At each step, I'm going to do a matrix vector multiply. Then I'm going to run modified Gram-Schmidt to make that new vector orthogonal to all the previous vectors. And then I'm going to divide W by its norm, and I'm going to save all the coefficients in this little k plus 1 by k matrix H. And when I'm finally done, I'll solve a least squares problem with this tiny matrix, and I'll get the answer from that. So what's the new algorithm? In one step, I'm going to compute what is called the matrix powers kernel. I'm going to compute V, AV, A squared V, dot, 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 and I'm going to show you how to minimize the communication in there. That's going to give me a different basis for the same subspace that I had over here. I still need an orthogonal basis to run GMRes. So how do I get an orthogonal basis? I'll just run tall skinny QR, which I already told you about. So that's going to give me, so the columns of Q are going to be the same as the columns of V. And it turns out that's enough information to rebuild this matrix from the R factor, and then I do the GMRes as usual. So that's how that's going to work. So there's a sequential case. The number of words moved decreases by a factor of k. And in the parallel case, the number of messages decreases by a factor of k. So does anybody see why this is completely numerically unstable? Even though it's the same answer in exact arithmetic.
W matrix.
Yeah, this becomes, all these vectors become parallel to the dominant eigenvector, and you lose all the precision. So here's the fix. We're going to replace these polynomials, a squared, dot, 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 by other polynomials. And for a little bit of extra cost, I can make sure that these are not nearly parallel to one another. And by doing this, we get good answers, and we got 2.3x speed up for GMRes and a 4.2x speed up for BiCGStab. I'll talk more about that algorithm later. So let me just show you what goes wrong if you don't pay attention to numerical stability. So here is a particular convergence plot of classical GMRes. So the vertical axis is the norm of the residual on a log scale and iteration count. So that's the original GMRes. So what about the algorithm I just showed you? There's its convergence plot. It doesn't converge at all. Okay, and what if I choose a different basis? It does just fine. And we're calling that the Newton basis. And so basically, what do you do from all of those polynomials? You're sort of implicitly running Arnoldi. You can get information about the spectrum of A, and you can use that to build the right polynomials to ensure you get convergence. So we're sort of doing a little eigenvalue problem under the hood. Okay, so now the question is, how do I get this savings from computing AX, A squared X, A cubed X in one step? So I'm going to draw you a picture for the simplest case, a 32 by 32 tridiagonal matrix that's small enough that I can draw you every detail. And so each of these dots represents all the entries of X. Those dots represent all the entries of A times X, and I want to compute A squared and A cubed. Okay, so what's the dependency graph? It's a tridiagonal matrix, so that entry of A times X depends on those three entries of X. And I'll just draw it that way to make it easy to draw. And of course, this dependency graph appears everywhere, so that entry of A cubed depends on those entries of A squared. And if I just keep expanding the dependency graph, eventually it depends on all those entries of X. And of course, I don't want just one entry of A cubed, I want a bunch of entries of A cubed. So that's sort of the dependency graph that I have to worry about. So let's suppose in the sequential case, my cache can only fit 1/4 of all the data. So what can I do if I can only do that? I'm going to read in the first quarter of the entries of X, the first quarter of the rows of A, and that gives me enough information to compute that trapezoid. The next step is, and all of this, there's no more memory traffic here. So now I can read the next quarter of the entries of A. I need to save a little information here from the border, and then I can compute everything in the red parallelogram. And then I can do the green, and then I can do the yellow. So that's the sequential algorithm in this very simple case. So what about in parallel? So let's suppose I have 4 processors, and processor 2 is going to be responsible for everything in that little block. And so what's its dependency graph? It needs to know all of these. So what would the classical algorithm do? I'd have one message to send that to there, one message for that, and one message for that. Instead, what I'm going to do is send all these 3 at once, and the processor 2 is going to recompute everything in that trapezoid. So all of this information is going to be computed redundantly. Processor 2 is going to compute it, and processor 1 is going to compute it. But when this is a very large matrix, this is tiny compared to everything else. So it's a lower order term. And so this is what each processor is going to do. Processor 1 will compute everything in there. Processor 2 will compute everything in there. And all the triangles will be computed redundantly. So how does this work for a general sparse matrix? So let me draw a general sparse matrix. Each vertex is a row or a column, and this is a symmetric matrix, and each edge is a non-zero. And somehow I've partitioned it so that each into this into these blocks with these dotted lines. So let's suppose one processor is responsible for computing all of the entries of x and ax and a squared x and so forth that correspond to these particular rows. So what information does this processor need from its neighbors? Well, to compute a times x, you do one step of breadth first search. You go out to get your nearest neighbors. To compute a squared, you go out one more neighbor. And to go out to compute a cubed, you go out one more neighbor. So as long as I've partitioned this in a way that there are not very many edge crossings, then this will minimize communication. And so this is a classical graph partitioning problem that people have optimized for a long time in computer science. And then I also have to pick, in the sequential case, what order do I do these in? Because I would like to reuse the data as much as possible, and that turns into the traveling salesman problem, which again we can solve approximately. And so this same idea works for general sparse matrices. And in completely independent work, there was a paper just published which also won a supercomputing prize paper where they optimized this even further to minimize the communication. So there's been some interesting recent developments in this. So the last slide on these problems, I just want to, this is just eye candy. I want to show you what happens to BiCG-stab. So this is the classic algorithm for BiCG-stab. It has a couple of, several matrix multiplies in it, matrix vector multiplies, and a bunch of dot products and Saxbys. So I want to solve AX equal B, and with the Krylov subspace method, and this is biconjugate gradient stabilized. And this is one of the many Krylov subspaces in the big design space. It's very popular to use for non-symmetric problems. So this is just eye candy. So the question is, how do we have to reorganize it in order to use the kernels that we talked about? And this is what the new algorithm looks like. And so it turns out that these two matrix vector multiplies turn into 3 calls to the matrix powers kernel. And all of these dot products turn into 1 matrix multiply, which we also know how to parallelize very well. And then after all this algebra, you get exactly the same answers that you got before. So this is I'm just saying the algebra is complicated, so it requires some innovation. Yes?
You told us about the matrix powers kernel, but what about the Newton polynomial?
So all I need to do is take an appropriate linear combination of ax and a squared x, and so that gives me p2 of a times x. And then I take a linear combination of these 3 and these 4, but I have them all sitting in memory, so these are just local Saxbys.
You do first compute all of
them. No, I compute them. So what I can do is compute them on the fly. So this would be, ax, this would be p2 of a times x, this would be p3. So I'll just take different linear combinations as I move up. Yeah, so it's all a little bit of extra local work.
These Newton polynomials are nested, yes, so that each time you're adding a new root, that you're keeping the previous?
Yes, right, yeah. The details are in Aaron's thesis, so I have to go.
But they're like custom poly. It's not just like a Chebyshev recurrence or something.
Yeah, it depends on, so we're sort of, implicitly, getting an approximation of the eigenvalues as we proceed.
So I guess if you're replacing the regular matrix products, presumably if you just counted the number of matrix vector products you're computing, there's more of them.
No, it's the same. So at each step, I'm going to, so let me get, where did I have this? So I'm going to, P2 of A is going to be come from multiplying A times P1, or some linear combination of the previous ones, and that'll give me P2. So it's,
But do you know P2 in advance?
I'm going to be computing its coefficients on the fly based on estimates of the spectrum of A that I get from this information.
When does that happen in the algorithm? Which processor does that?
Well, everybody can do it independently because it's just a little bit of local work.
So but every processor can know the result of that based on only their information?
Yes. Yes.
Yeah,
Why is it that the processor all the way on the left and the processor all the way on the right can agree on the polynomial from having looked at completely disjoint data?
So we have. So I'm going to have to refer to Aaron's thesis for details, but I don't think any communication is required to do that. Yes?
Can you prove something rigorously about the condition number of W?
Yeah, I don't think, again, I have to go back and look at her 2015 thesis. I'm not sure, so. Yes?
This algorithm seems to require k to be related somehow to the degree of the graph. Is that a...
No, this is, well, I mean, so the question is how many steps, so k is a tuning parameter. And I have other slides, which in another talk that I don't have here, where we adjusted k, depending on the sparsity structure to get the optimal speed up. So it depends on the sparsity structure.
Oh, okay. So you might use this and then you might do this parallel computation procedure multiple times in a row if you need CG to convert over.
Yeah. So k, think of k as being, order 5 or 10.
Okay.
So we will save a factor of 5 or 10 in the communication of this kernel, but then we have to do it over and over again.
Okay, so I should imagine this as kind of still like a two-loop algorithm in some sense.
Yes,
an outer loop of CG conversion.
Yes.
And an inner loop doing 5 iterates at a time.
Yes.
Okay, cool.
Yes.
Thank you.
Sorry, that was not clear. And that was certainly done in these practical implementations here that got these speed ups. Okay, finally we go beyond linear algebra. We'll see how long it takes. So what I'd like to do is show how this extends to optimal algorithms for arbitrary code that looks like nested loops accessing arrays. But before I do that, I want to sketch the proof just for matrix multiply that we're going to generalize completely. So here's the counting argument. So suppose I'm just doing the sequential case. So I have a local, well, this is sequential or parallel. I have a local memory of size capital M, and so I'm only allowed to have an M number of local data. And so what I need to do is figure out how much progress I can make in my algorithm, how many multiply adds can I do if I'm limited to M words of data. And I'm going to call that F. All the math is going to go into bounding F. So that means in order to finish the algorithm, I need to refill my cache, the number of iterations that I need to do, so n cubed divided by F times to complete the algorithm, to do all of my n cubed operations. So how much does it cost to refill the cache? Well, it's M, because that's how big the cache is. So this is the number of reads and writes. And I'm ignoring the constants that people care about. So M times the number of iterations divided by the maximum amount of work I can do given M words of data. And so what I'd like to do is somehow, so I know that's n cubed, I know that's the cache size, so I need to bound F. And so what I'm going to do, unlike Hong and Kung, is use a geometrical argument that's going to generalize to sort of arbitrary algorithms. So I'm going to represent my algorithm geometrically as a three-dimensional cube. So this is an n by n by n cube, and there are three indices, I, j, and k, corresponding to the three loop indices. And so this face is indexed by I and k, and those are the subscripts of A. So each one of the squares in this face represents an entry of A. So that's A11, A21, and so forth. That's the B face, and that's the C face. So what do the cubes inside represent? They represent the operation. So what does that cube need in order to do its work? It does, this cube here is doing C11 is updated by A31 times A13 times B31. So it needs the data on the three faces. And so what I'd like to do is say, if I can have M squares on this face, and that face, how many cubes can I have? That's sort of the bound that I want to make. And so here's the simplest way to get some intuition. So here's my square. And let's suppose I want to do that particular brick of cubes in the middle. So it's x by y by z. What data do I need? Well, it's these three projections. So I need that z times x block of A, that y times z block of B, and that x times y block of C. So how many flops are in there? That represents x times y times z flops. How do I relate that to those number of entries of A, B, and C? Well, just multiply their areas together, take the square root, and it's equal. So that is what's true there. And what's amazing is that it's always an upper bound. And this is a theorem that goes back to 1949. So I can have an arbitrary subset of cubes in here. I project them onto the A face, call it the A shadow, the B shadow, and the C shadow. And the number of cubes is upper bounded by the product of the areas, take the square root. And that's true no matter what subset there is. So that's where my m to the 3/2 comes from. OK, so the number of loop iterations doable with m words of data is the number of cubes. So that's going to be how many entries of A can I have at most m? At most m entries of B, at most m entries of C. I'm ignoring all the constants here. So it's m times m times m, take the square root, and that's f. That means I need to read and write at least this many words of memory, and I get the Hong Kong lower bound. Much more simply, I think. OK, and so what this abstraction lets you do, we didn't pay attention to the dependency graph of the algorithm at all. We just said, my inner loop looks like this. And it applies to any code that smells like 3 nested loops. So matrix multiply, all the BLAs, LU, QR, tensor contractions, which can have a lot more nested loops. It can apply to whole programs, like sequences these operations. Like I'm computing powers of a matrix multiply. It's the same lower bound. It also applies to both dense and sparse matrices. So the numerator doesn't have to be n cubed. It's still, I'm only doing a subset of the interior, but I can still do at most, m to the 3/2 work, at any time. So so the only thing that changes with the lower bound is n cubed changes into the number of flops, which depends on your sparsity structure. It applies in both the sequential and the parallel case. In the sequential case, m is your cache size. In the parallel case, it's your local memory size. And I don't have to do multiplies and adds. I could be doing something like Floyd-Warshall, which also is basically matrix multiply, but it's sums and maxes and stuff like that. Yes? Was the question? Oh. OK, and this won another Best Paper Prize. So homework 6. Since I already told you somebody won a prize for this, what is the best possible constant in the lower bound? Yes?
Are we trying to upper bound f? To give a lower bound on the...
Yes. Yeah, I want an upper bound on f. What's the most work I can possibly do?
Okay.
And
this inequality is going the wrong way, is it? But I would have expected we need like an A and B
So I'm going to use the number of loop iterations is upper bounded by f, which in this case is m to the 3/2. So f is I'm using m to the 3/2 as my upper bound and how much useful work I can do. I can't quite do that much because obviously this is 3m. M plus m is too big to fit in cache, so it's has to be a little smaller. So there's a different constant there. But this is still basically how much useful work I can do.
Didn't we define f as like the most work we can do with bounded memory?
Yes, and that came from saying I want to bound the volume of that set. That's useful work, the number of cubes in that set. And I'm going to be limited by Loomis-Whitney by this formula, which is the number of entries of A times the number of entries of B times the number of entries of C. Square root.
F is the volume of the
yes.
cube, right?
Is the volume of that blob, whatever it is.
And that's this product of the shadows.
Yes, which is upper bounded by
But something like the
m.
sum of the shadows is our memory.
Yeah, that's a constant. Yeah, that's where you get into the constants, which is the homework assignment. But I'm just doing very simply saying I can't have more entries of A than M because that's the size of the cache. Ditto for B and ditto for C. And of course, if I have them all 3 in there at the same time, it's smaller by a constant factor. But I'm just trying to not worry about the constants and leave that for homework. Yes, what's the best possible constant factor? OK, so how does this generalize to arbitrary code? So let me just write down what I just did. So here was my model. I had 3 nested loops. I had 3 arrays, and they had some subscripts. And I got this lower bound. So this is what I want to generalize this to. I'm going to have some iteration space in k dimensions. So I have some set of k tuples of integers. It doesn't have to be k nested loops. It's just some arbitrary set. And in the inner loop, I have a bunch of arrays that I'm going to access and do something with. And they can have whatever subscripts you like that are linear combinations of all these loop indices. So that's my general code. And that includes lots of algorithms you'd never write down, but it includes a lot of useful algorithms. And so here's the theorem. The number of words moved is lower bounded by the number of loop iterations, n cubed for matrix multiply, divided by the cache size to some magical exponent, which was 1/2 for matrix multiply. And so where does this magical exponent come from? What does HBL stand for? It stands for the Holder-Braskamp-Leap inequality. So, which is a famous, theorem from functional analysis, and it was originally proven, to bound, volumes using areas, the one I showed you, but it was extended by my collaborator on this, Michael Christ and Terry Tao and others, so you could work over discrete abelian groups and count lattice points, which is what you need to do for communication theory. And so we have an algorithm that will actually compute this. And that's a whole nother talk if people are interested. And one of my graduate students proved exists an optimal tiling that attains this lower bound, no matter what weird code you write. And so let me just show you a picture of what this looks like. I'm not going to prove any of this. So let me take a really simple code, 2 nested loops, and I want to compute all possible interactions of A sub I and B sub j. So you could think of this as computing the potentials or something from particles. So here's a picture of the iteration space. Each point on this axis represents an entry of A. Each point on this axis represents an entry of B. And each dot in the middle represents a particular iteration. So what do I need to do to execute that entry? I need that entry of B and that entry of A. So those are the projections. So what I'd like, let's suppose my cache size is of size, and let me just simplify this. All I care about is I'm accessing A sub I and B sub j.
We can wrap up in like a minute.
Okay. Okay. So let's suppose that I only have a cache of size 10. So what's the optimal tiling? I'll read in 5 entries of A, 5 entries of B, and I can do all 25 entries there. So you don't need any fancy math to do that. And I can tile the plane, and that's my optimal algorithm. And all the ideas I had about 2.5D apply here, and I can get big speedups, and we've used them to accelerate transformers. So it's the same idea, but I won't go into the details. So let's suppose I make it a little more complicated. So now my subscripts are I and I plus j. I still want to read in 5 entries of A, 5 entries of B, and do 25 pieces of work, and there's my tile. And I can also tile the plane there. And so that makes sense. But now, let me make it a little messier. So I said it should work for arbitrary subscripts. So what is the optimal tiling? It looks like that. 5 entries of A, 5 entries of B, and I can do that. And that sort of tiles the plane, but not quite. So what do I do about all the dots that aren't covered? All I have to do is take this picture and shift it up by 1. I can do those. Shift it up again, shift it up again, shift it up again, and I finally have tiled everything. And this is group decomposition theory. So this is what it depends on. And so what's left? Lots of open problems. Dealing with small loop bounds. So what happens if you're doing a skinny matrix multiply? We have answers for that, at least in the simple case where the subscripts are I and j. Dealing with dependencies. I have a conjecture on how to generalize Holder-Braskamp-Leap to deal with dependencies. That's another talk. We have some results for sparse matrices, but it obviously depends on the sparsity structure. Dealing with variable precision, dealing with network topologies, dealing with the fact that writes can be sometimes much more expensive than reads, sketching, and compilers. And it seems like I should do the demo of where of how the compiler will do this automatically for you some other,
Sure, maybe in the working group.
Yes, okay. So that's it. And it all works for convolutional neural nets. So that we have an optimal algorithm for that.
We have time for one question. We had many during the talk. Yes.
The sparse algorithm, is it... Suppose I give you a sparse matrix that has like 1 dense row or 1 dense column. Is there any recourse?
So it depends on the sparsity structure. What results do we have? Let me just answer that. So one paper is if you have Renyi matrices, where each entry is randomly IID sparse or not, and there's a lower bound that is true with high probability, so we can tell you how that works. And if you have a matrix which is well partitioned, so think of a 2D mesh or a 3D mesh from typical finite element problems, in that case you can prove that the bottleneck in communication is just the trailing dense submatrix when you find for the last graph separator. And if you just use the correct dense algorithm on that, you'll hit the lower bound. So there's a whole bunch of interesting structured cases like that.
So like you can split the graph up into the good sparse stuff and a little bit of dense chunk at the end?
Yes,
something
right.
like that?
And that's
Okay.
true for lots of problems that come up in practice.
Cool.
The 2D mesh being the simplest one to understand.
Okay, great, thank you.
Thanks a lot, Jim.
Okay.
Our last talk for today, but there's a very important activity in the afternoon, which is the working groups. And in this activity, we're going to